Welcome to Library Seminars, NOAA Central Library's webinar series for the presentation of research and ideas that reflect the National Oceanic and Atmospheric Administration's mission. Today we'll hear from Dr. Cameron Hodgson, who will be introduced by the organizer and host of the series, Kristen Blackheart from the Office of Science and Technology. His presentation, Incorporation of Environmental Effects into Stock Assessments and Habitat Modeling, Lessons Learned from American Lobster in the Gulf of Maine, is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries. Before I hand over the mic, here are just a few announcements. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I will add the channel's link to the chat box once the presentation starts. Our speaker shared his slides, so please feel free to download them from the handouts menu in the webinar control panel. That's most likely on the right side of your computer. And most important, we are very interested in your questions and we encourage you to ask them throughout the seminar, even though the speaker will not address them until the end of his presentation. All audience members are muted, so just go ahead and type them in the questions chat box located again in the webinar control panel. So with that, let's get started. The mic is yours, Kristen.
Thank you, Lisa. Our speaker today is Dr. Cameron Hodgson. Cameron just recently received his PhD from the University of Maine under the advisement of Dr. Yong Chen, working on a project that was focused on climate effects in scallop and lobster modeling processes. He is now a postdoc at Stony Brook University School of Marine and Atmospheric Sciences, still working with Dr. Chen. His current research is focused on simulating the Gulf of Maine lobster fishery under different management and climate scenarios. Thank you very much for being with us today, Cameron. We're excited to hear about your research, so take it away.
Hi, well, thank you for that introduction, and thank you everyone for tuning in. I am, of course, Cameron Hodgson, and today I'm going to be discussing the broad topic of how to incorporate environmental effects into stock assessments and habitat models. So the presentation today is going to be split into three main parts. Part one will focus on how to test the necessity of inclusion of environmental covariates in survey indices for use in stock assessments. Part two will discuss how to derive environmentally explicit recruitment patterns and incorporation into the stock assessment process. And part three will shift gears a bit to discuss potentially unexpected or unanticipated challenges of mapping and forecasting habitat for non-data rich species. Throughout most of this work, I will be talking about lobster, but a lot of the methods I'll go over have a wide applicability, especially for crustaceans or length-based assessments in general. So this is part one, discussing some work that we had published in the Canadian Journal of Fisheries and Aquatic Sciences, a framework to incorporate environmental effects into stock assessments informed by fishery independent surveys, a case study with American lobster. So this research is predicated on two facts. The first, marine life is affected by the environment. Easy freshman year 101 stuff, but this is a key concept. Stock assessments for many economically important species have so far not really considered the environmental effects. In the old world, that was okay. You know, why consider environmental effects if these effects are static or unchanging year to year? It wouldn't affect assessments and it wouldn't affect results. Which leads me to point number two, the environment is changing. It's warming. These species are changing to adapt or they're dying. Their movements, their physiologies, their life histories are all now changing in this new world. The need to account for these effects inside stock assessment frameworks has never been higher and is only growing as consequences of false assumptions can lead to devastating effects concerning fish populations. So this study really set out looking for a way to aid stock assessment scientists and fisheries managers to incorporate these effects, but we didn't want to completely overhaul current methodologies. We wanted a simple and effective method that could be used with existing assessment frameworks to incorporate these effects. So many stock assessments utilize what's known as an abundance index, a representation of catch from fishery independent surveys meant to infer changes about the larger population. Now, the accuracy of these indices is tied to environmental drivers that affect both the target species abundance and the catchability of the surveys. And this is the aspect of stock assessments that this research framework targeted. So we have developed a framework that stock assessment scientists can follow to test the necessity of incorporation of environmental covariates on a species by species basis. The best part is that our framework is totally independent of the stock assessment model itself. It works in tandem, only manipulating the abundance indices before they're used in the assessment process. And this part of the presentation is meant to outline how. So current or traditional methodologies concerning the American lobster stock assessment are relatively simple. There are bottom trawl surveys run by different state and federal agencies throughout the Gulf of Maine. Now, survey catch data on lobster has been long recorded as far back as the 1970s. This catch data is used to estimate abundance indices over time, which is like a quantifiable estimation of the trend of change in the population. This, along with other information from the surveys, information from the fishery itself, and biological data, are used to fuel the assessment model, which generates, among other things, reference abundance over time and exploitation rate over time, as well as various model diagnostics. I'll get more into those details in a little bit, but first I wanted to show our addition to this framework. So now using this new set of steps, abundance indices are not simply raw survey data, but they're transformed and recalculated inside a delta generalized linear mix model, or delta GLMM. The survey data, along with detailed temperature and depth data, are used to create these new indices, which we refer to throughout as modeled indices. So let's break down how this process works. First, the delta in delta GLMM refers to its two-step process, where these factors here are used to calculate first the probability of a lobster at a given location in the Gulf of Maine, and then the probability of catch given that lobster is present. From these calculations, we can then estimate species density at locations throughout the Gulf of Maine known as knots, which can be thought of like spatial points that are a proxy for a bounded spatial area. Again, walking through, so these effects are estimated in the delta GLMM using catch data from the bottom trawl surveys. Temperature and depth effects can be matched to both trawl stations and to knots, allowing for estimation and extrapolation of species density. These parameters can be used as either density covariates or as catchability covariates, but the same covariate shouldn't be used as both types in the same model run for fear of model inflation. So these parameters are used to calculate the linear predictors in the middle column, and then after catchability effects are dropped, species density can be extrapolated throughout the Gulf of Maine. From the spatial density, an abundance index can be generated by integrating over space, and we can calculate coefficients of variation in this process so as to estimate the reliability and overall precision of the indices generated, and to be able to sort of directly compare them to the traditionally used indices. And lastly, it's important to note that this delta GLMM we created was created using Jim Thorson's vector autoregressive spatiotemporal, or VAST, package in R. So that is how we generate these new modeled indices. How do we actually use them? So let's break down each of these sections here. First, the assessment model. The assessment model we use is a seasonal model, meaning we have data for 4 time chunks throughout the year, winter, spring, summer, and fall, each with its own set of dynamics and parameters. This model is length structured, so lobster age is difficult to quantify, and therefore it's quite unreliable. So a length-based model is more appropriate than an age-based model, which might be more typically used with finfish species. Now, for the sake of time, and because it's not really the focus of this particular study, I'm not going to go into the details of the assessment model, but they can be found in the publication for those of you who are interested. Now, the assessment model generates two major forms of diagnostics that we used to compare model results, objective function value and Mons row values. So the objective function value is the summed value between the differences of observed and calculated values throughout this process, such as observed and predicted fleet catch, or observed and predicted survey catch, or size compositions. And because it represents differences, the goal is to minimize this value. So the smaller the objective function value, the more representative the model results are of the real world. Mons row values might be new to some of you. So the assessment model runs from the historical period up to the present and generates values for spawning stock biomass, fishing mortality, and recruitment over that time period. A perfect model may calculate the same values for spawning biomass, fishing mortality, and recruitment over that time period, even if some of the newer years, some of that newer data were missing. This is essentially impossible. You're never going to find this. So the differences that can be seen because of this are what's known as retrospective bias. So Mons row is a way of sort of quantifying this bias. And like the objective function value, we want Mons row values to be minimized, as this represents a low retrospective bias and overall more reliable model output. And apart from these diagnostics, we also wanted to look at reference abundance and reference exploitation rate, because these values are directly used to calculate stock status for the fishery. So by using the same criteria to calculate biological reference points for each of these, and then seeing how the total number of individuals or fishing pressure changes year to year in relation to this stock, we can see how stock status changes over time. Is the stock overfished? Is overfishing occurring? We did this so as to ask the question, if indices using environmental covariates had historically always been used, would there have been differences in management and regulations as a result? So before we actually move on to the results of this particular study, let's recap quickly the methods and the actual objectives. So there were 9 total combinations of temperature and depth as density or catchability covariates. So that yields 9 total different modeled indices, plus the traditional design-based indices, for a total of 10 scenarios. And we compared precision of these different indices directly using the coefficients of variation. For each of the 10 scenarios, we compared objective function values and Mons row values outputted from the assessment model. And again, to note here, the indices with the accompanying CVs were the only thing changed in the assessment model between model runs. We also calculated BRPs so as to compare differences in stock status over time between the scenarios. And the goal here was to infer the necessity of modeled indices for the American lobster stock assessment in the Gulf of Maine using these environmental covariates, based on whether they changed results and whether they changed results positively and significantly. So first, a big positive, all CVs for the 9 modeled indices were much lower than the traditional CVs for the design-based, meaning that they may perhaps be more precise or more reliable. This definitely sort of highlights the property of variance reduction in geostatistical models like the delta GLMM that we used. But however, moving on from here, there's sort of a band-aid that needs to be ripped off concerning the rest of the results. And that's that none of the 9 scenarios actually showed improvements to model fit. And those that showed improvements to retrospective bias were pretty minimal. So let's look at the data directly. As you can see here, the top is a graph of objective function values graphed by their differences to the objective function value in the design-based scenario. And all are larger, ranging from roughly 10% to over 40% larger. This denotes that these models did not have as good a fit as the design-based model did. For the Mons row values, it's a bit more interesting. So the bottom is a graph of the values for spawning biomass, recruitment, and fishing mortality across those scenarios. And the first column is the design-based values. What appears to be happening is that Mons rows for SSB and or responding biomass and recruitment are usually lower, but Mons row for fishing mortality is much greater. So this may point to an offset in the assessment model when these indices are used, where the model is simply sacrificing retrospective biases from biological or population aspects to fishery aspects. Needless to say, fishing mortality calculations seem to be very unreliable when using the modeled indices. But so we chose the model with the lowest Mons row values relatively and compared it to the design-based. And here we have reference abundance for both over the time series with their respective BRPs marked. So the colors indicate status in relation to the reference points, solid lines here representing target references and dotted lines representing threshold references. And there may be some similar trends between these, but it's definitely easier to see the disagreement between the two. And we did the same thing, but with exploitation rate here, and the differences are astounding. It's noteworthy to point out that the model had trouble with fishing pressure in terms of retrospective bias, and this seems to point to that same problem again. So now we have to ask ourselves, do we recommend the use of modeled indices with environmental covariates for the stock assessment of Gulf of Maine lobster? Well, no. The use of modeled indices just seems to shift things around. The fit becomes a bit worse, while retrospective patterns might be better, but only because of this offset of population versus fishery parameter estimation. So we conclude that they're not necessary. Modeled indices do not seem to improve the American lobster stock assessment of the Gulf of Maine. But why? Perhaps why this didn't work is actually a bit more fascinating than the results themselves. Our hypothesis is survey coverage. So lobster are, I guess, special. Of the many marine species out there currently targeted and caught in fisheries, lobster have an incredible amount of data. In the Gulf of Maine stock area, there are virtually no gaps in survey coverage. Inshore areas, offshore areas, shallow, deep, they're all surveyed in one capacity or another. And the amount of effort over time is astounding, well beyond the available data from most other fisheries. But if anything, this should mean that we have a lot of data to work with and that our calculations should be more reliable. So why isn't this what we're seeing when we use modeled indices? Well, it's because of what modeled indices are meant to do. Geostatistical models like our Delta GLMM are made to extrapolate data into unknown regions and unknown times using spatial and spatiotemporal parameters. They're meant to sort of fill in gaps in the data. But with lobster, there's not that many gaps to fill in, which brought us to the following conclusion, that the bottom trawl surveys in the Gulf of Maine may be capturing trends in the population already that we were directly trying to estimate with our Delta GLMM. Now, this greatly supports survey efforts and makes the realization that good modeling efforts are not always a substitute for good data collection. That being said, I said that lobster were special, and that brings me to another important factor. This conclusion is not universal. So any stock assessment that utilizes abundance indices from fishery independent surveys can follow our methodology step by step to test if the inclusion of environmental parameters in modeled abundance indices is necessary. The added bonus now is that this research now comes with a warning. Every species is different. The need for inclusion of these parameters will change. Just because a technique is more advanced does not necessarily mean it's going to yield better results. However, the only way to test it is species by species. So to quickly summarize this section, modeled indices with environmental covariates did not improve the assessment for Gulf of Maine lobster. It's important to note that this does not mean null relationships of lobster with these parameters, only that the abundance indices currently in use might already capture appropriate trends. Temperature and depth effects on other aspects in the lobster stock assessment might still improve the overall model, but these results are not saying that they won't. And these results will vary species by species. For lobster, we now know that inclusion is not necessary, but this does not give us any information on other species or other assessments. And any and all interested parties can follow our methodology to test this framework on their species or their assessments, and we highly encourage it. Okay, now on to part 2, using recruitment-related input parameters to test inclusion of thermal habitat in lobster stock assessment and forecasts. So biological reference points, which we were introduced to earlier, or just reference points, are target or threshold calculations of a given stock or population that trigger management actions when reached. For example, this calculation may be percentiles of historical abundance. So these values plotted here are simply the 25th and 75th percentiles of historical abundance estimates. If the population is above the 75th percentile, it's in good condition, and if it's below the 25th, it's in bad condition. What might be wrong with this current setup? Well, those black lines are static. They don't change over time. As I've said before in this presentation, and I will say again before the end, the environment affects these estimations, and ignorance of these effects may lead to spurious management measures. So how do we get around this? Well, first we need a quick lobster life history lesson. The amount of spawning biomass, or the number of breeding females, should theoretically have a relationship with the amount of larvae or offspring in the population, known as recruitment. Biological recruitment are those larvae. Model recruitment is the minimum size lobsters used in the stock assessment for the species, which is 53 millimeters carapace length. So establishing a useful spawning biomass recruitment relationship for lobster would have to link spawning biomass to model recruitment. If such a relationship was discovered, then management would be able to determine how they would have to manage spawning biomass today to have the desired levels of recruitment that they want in the future. And because you can directly enforce conservation measures on adults, on females, but not so much the newborns, the larvae. But previous studies have tried to estimate a spawning biomass recruitment relationship for lobster and concluded that the relationship is probably very spatial in nature and therefore pretty challenging to derive stock-wide estimates. But this work set out to see if some combination of temporally dynamic environmental variables, namely thermal habitat, affected this relationship and could be used to create stock-wide predictions. Such a temporally dynamic relationship would allow for something like the bottom plot here, where each year spawning biomass would be in a given range to reach desired future recruitment levels. Unlike the above plot, which might be biologically unrealistic as it has no effect from the environment changing around it. So in this process of determining a temporally thermally dynamic spawning biomass recruitment relationship for Gulf of Maine lobster, we arrived at 2 variables. The first was temperatures during the fall spawning event, which we called LM. And the second was temperatures during a lagged 3 to 5 year developmental period, which we called DM. Now, this led to a model with a deviance explained of nearly 90%, meaning that it accounts for a lot of the variation seen in the SSBR, or the spawning biomass recruitment relationship. And this is what the influence of spawning biomass and the other 2 thermal habitat variables looks like on recruitment. So green areas here represent combinations of spawning biomass, LM and DM, that lead to management desired recruitment levels, and red areas do not. Essentially, high DMs, low LMs, and high SSBs produce high recruitment levels. Using that relationship, we can produce these plots. So the blue lines represent the differences between recruitment from the level of SSB on the x-axis and the level of management desired recruitment. In this case, 557 million individuals. So when the blue line is above the dotted y=0 line, then that level of SSB will lead to at least 557 million individuals of recruitment. And each plot is for a different year, indicative of different yearly fluctuating thermal habitat parameters. And thus the plot changes between years because of these changing environmental covariates year to year. So this model may prove useful for future management of lobster. Recruitment calculations from spawning biomass are very sensitive because they're very environmentally driven. They seem to change more from the environment than from spawning biomass itself. Now, future research should see us sort of combine this work with previous studies which indicate the more spatial nature of the SSBR relationship. And this developed dynamic biological reference point calculator can be used for a lot of different crustacean stocks, not just lobster. So yeah, that dynamic reference point calculator has a lot of potential applications, but that spawning biomass recruitment relationship for lobster is also something that may allow for advancements in a lot of different aspects of lobster stock assessment. That includes being able to use spawning biomass and forecasted temperature to predict future recruitment levels. But how do we look into the future? What tools do we use to do that? Well, in an ideal world, we would just have something akin to a magic lobster crystal ball that could predict what the future of lobster in the Gulf of Maine will look like. Well, we kind of do have something like this. It just looks a lot less magical. So that was a quick snapshot of some code from a projection model I designed for American lobster, which utilizes this equation. So output information from the UMaine stock assessment model, which is the assessment model we've talked about thus far, is coupled with estimating fishing rates and recruitment to calculate the biomass of the next season. And this is an iterative process, repeating itself every season with parameters changing based on seasonal differences. And so the model can estimate seasonal and yearly changes in total lobster biomass. A big piece of this puzzle, though, is the environmental data. And we can incorporate that spawning biomass recruitment relationship into the forecasting framework here. And now we have a thermally explicit forecasting model for Gulf of Maine lobster. Now, recruitment estimations can be done iteratively based on calculations of spawning biomass and user input environmental variables, which have been forecasted a priori. Was this actually necessary is the question that we wanted to ask. So what do stock projections of lobster look like under a thermally explicit scenario versus one that doesn't include environmental effects? And how does this compare to those derived in actual stock assessment? Does it underpredict or does it overpredict? Well, to answer these questions, we took the forecasting model and we fed it data up through 2013. And then we used it to forecast up through 2018. So we forecasted with and without thermally explicit recruitment estimations. Doing this would allow us to compare these, again, projections, which are now technically hindcasts, to the data that was generated by the latest stock assessment done by the Atlantic States Marine Fisheries Commission. But before we compare trends to those generated by the ASMFC, let's first compare projections between the two forecasting model runs. So here, the upper left plot shows the differences in trends. So seasonally, they appear similar, with rising biomass due to recruitment events and falling biomass due to increased fishing pressure and natural mortality. Scenario 2, which is the orange line, is the environmentally explicit scenario. And the blue line, scenario 1, is the one without temperature effects. So it appears that the addition of these environmental covariates changes the trend of stock biomass over time, the dotted lines, from decreasing to increasing. Looking at the other plots, The effect seems to be almost sort of compounding over time. Each consecutive plot going in a Z formation is fitting a regression line of one less terminal year to the data. So as more years are added into the forecasting analysis, the further the future estimates of stock biomass diverge from each other. This indicates that ignoring environmental effects on recruitment may cause an underestimation of future stock biomass. And this plot shows how recruitment estimations over time produced by the model compare with those generated by management, which is the green line. So if you focus on the trends again, the dotted lines, not including temperature effects, it seems to underestimate future recruitment sizes, which is the blue line, whereas including temperature alone as a recruitment covariate seems to overestimate recruitment estimations, which is the orange line. Why might this be the case? Well, temperature itself, from what we've seen so far, seems to have a net positive effect on recruitment. As the Gulf of Maine warms, recruitment sizes may continue to rise. However, there are other unexplored effects that seem to combat this increasing trend. Things such as increased disease, predation, or other environmental covariates. What we are assuming is true recruitment from the ASMFC lies higher than the forecasting model with no environmental variables, indicating that other variables are necessary to capture population trends. However, temperature alone overestimates recruitment, indicating that myriad variables would impact these calculations. And so future research should target other variables than temperature to see if a more comprehensive list of effects can be determined that can be used to more accurately forecast recruitment for Gulf of Maine lobster. Okay, so we've looked at a couple ways to test incorporation of environmental drivers in stock assessment through survey indices and spawning biomass recruitment relationships. Let's switch gears from stock assessment to habitat modeling. So this is part 3, consequences of model assumptions when projecting habitat suitability, a caution of forecasting under uncertainties. So a given species of fish has an ecological and environmental niche that it prefers. It performs best in certain temperature waters, waters of a certain salinity, pH, etc. It may prefer waters where the temperature is too cold or too warm for certain predatory species, or it may prefer waters that allow for the best egg production. These places that this fish species prefers and lives are its habitat. But what happens when that habitat changes? If temperature rises too high for the species, it can be dangerous for it. This new environment may bring unexpected predators from different areas, which can lead to local extirpation. This new environment may cause the fish to move somewhere else in search of waters with cooler temperatures, which may cause shifts in other species distributions, including our own fishing fleets. Lastly, and most simply, extreme changes can also just cause the species to die. There's a lot of unknowns here, though. All of these people, recreational, commercial fishermen, researchers, divers, and even just people who like to eat seafood, are all sort of dependent on fish communities. Well, in a changing world and in an effort to mitigate impacts from these shifting distributions and assemblages, we need to be prepared for these changes. We need to answer the relatively simple question, under climate change, what will happen to marine life? Well, to answer that requires us to answer a different question first. What will happen to their habitats? If we can figure out and map the changes that these species' habitats will make, then we can make predictions about how these species will react and adapt to these shifts. So how do we determine how habitat will change? We can use something called a bioclimate model. This thing has many names, bioclimate envelope model, habitat suitability model, or simply habitat model. And here's how it works. First, a survey is designed that targets a given species. Over multiple years, the survey goes out into the ocean and samples for the target species, say, for example, cod. Over time, they're going to gather information about the areas that have the most cod, the least cod, where the cod are at different times of the year, how deep they are, etc. Well, any location and time has specific environmental conditions associated with it. every catch of cod has a depth that it was caught at, a temperature it was caught at, a salinity it was caught at. And likewise, locations with no cod are also going to have these same parameters, but probably different values for them. Well, if we can link catches to these environmental variables through some form of regression testing like generalized additive models, we can determine a predictive function for calculating cod catch or abundance from a given set of environmental data. Using this data, we can create maps of cod habitat as they exist today, but we want these maps for the future. Well, we need to figure out what future temperature and salinity values will actually be. So we have what they are today from systems like FVCOM, which is the finite volume community ocean model that was developed by UMass Dartmouth's SPS program. We also have anomaly data or change data from the IPCC, the Intergovernmental Panel on Climate Change. Now, the IPCC uses a multi-model approach to simulate changes to oceanic environmental variables like temperature and salinity. They make these calculations based on RCPs or representative concentration pathways. Now, these pathways are like different levels of climate change depending on how much more greenhouse gases we release into the atmosphere. So we take these anomalies and we apply them to our current environmental fields. We can generate a map of future fields. So a map of future temperature or future salinity in the year 2050 or 2100. Now, all we have to do is use the relationship that we determined previously using the generalized additive models and predict onto these future fields, and voila. We have a map of future habitat on a scale from 0 to 1. 1 being the most suitable and 0 being the least suitable. That may have been a lot all at once. So let's look at an example for, you guessed it, American lobster in the Gulf of Maine. So using the system we outlined, we can map current lobster habitat for this region, the Gulf of Maine and Georges Bank region. First, we need to establish suitability indices. Now, these are relationships of lobster to each of the 5 parameters we looked at, temperature, salinity, depth, latitude, and longitude. We did individual analyses for different seasons, spring and fall, sexes, male and female, and life stages, adult and juvenile, because we expected differences between these subgroupings. So we ended up with 8 total combinations. For example, adult males in the fall or female juveniles in the spring. So each of these plots is what is known as a suitability index. They represent suitability on a scale from 0 to 1 of a particular habitat variable. Using just these curves, we can see what ranges are most suitable for American lobster for each variable. For example, in the spring, they prefer temperatures around 8 degrees Celsius, but in the fall, they prefer temperatures around 13 or 14 degrees Celsius. So once we have these curves, we can move on to step 2. So once we have our current temperature, salinity, and depth fields from FVCOM, we can use those relationships to predict a habitat suitability index over the spatial domain. Now, a habitat suitability index is an average or a weighted average of the different suitability indices. And if we do that, we get this first map here. This is current lobster habitat suitability in the spring. Now, blue areas represent the least suitable habitat, green represents medium suitable habitat, and red represents very suitable habitat. And you can tell that inshore northern regions are very suitable, most likely due to a combination of shallow warm waters. And then offshore waters are less suitable, with very deep water out past Georges Bank not being suitable. This is what we expect to see, and it matches very nicely with where current lobster observations are. Now we apply the changes. So this map represents changes to lobster suitable habitat in this region. Blue represents a decrease in the next 80 years, and red represents an increase. And you can see that almost everywhere suitability is going to decrease. So what does future lobster habitat look like? Like this. So the same basic trends are still there. With inshore areas being very suitable, and then between Georges and Gulf of Maine being less suitable. But there seems to be this overall decline in suitability everywhere. The red inshore areas now appear more orange, and the offshore area out to Georges is now more blue than it is green. Using this map, we can make some predictions about changes to the lobster population. So eventually, if habitat continues to decline, there may be a similar situation here as in southern New England, where a recruitment collapse led to record low population numbers. Maybe these lobsters will continue to move further north into Canadian waters where it's cooler. But regardless of those predictions, that's the process. That's how you get these future habitat maps. So great, we now have future lobster habitat. We can just keep doing this for other species, and we can keep predicting their future changes. Well, yeah, that sounds great in theory, but is it a good idea in practice? Where in this process can things go wrong? Speaking from experience, there's a lot in this process that can go wrong, but today we're going to focus on the hidden things that can go wrong. The a priori assumptions that have to be made when running this bioclimate model. If these assumptions are falsely made, then the end results for forecasted habitat will be wrong, but given the limitations of the modeling framework, there's no way to determine the inaccuracy. So I'll be looking at 4 basic assumptions and discussing them each as they pertain to forecasting suitable habitat. Assumption 1, the importance of spatial scale. So in the Northwest Atlantic United States, there are 2 functional lobster stocks, the Southern New England stock and the Gulf of Maine Georges Bank stock. These areas are very large, and they span shallow inshore and deep offshore areas. These stocks are separated because there's little migration and recruitment sharing between the 2. But it also seems that different environmental preferences exist as well. So we looked at what happens when Southern New England data, or Southern New England survey data, is used alongside the Gulf of Maine data, and it increased spatial HSIs almost everywhere. So this is a map of differences between the base case and the run with Southern New England data included. Now, Southern New England lobster are subject to different environmental conditions. Different surveys cover different areas with different ranges of environmental parameters, and so lobsters captured in a given survey are only ever subject to the ranges that that survey operates in, which is why we see an overall increase in Gulf of Maine suitability, because in general, Southern New England has less lobster, so it inflates the Gulf of Maine data. And the same thing happens on smaller spatial scales. So when ignoring inshore surveys and extrapolating onto those waters, or vice versa, we saw some pretty odd longitudinal effects. As an example, offshore lobsters are obviously not caught in inshore waters, so those shallow depths may appear unsuitable when extrapolating onto them using the offshore specific data. This really highlights the need for appropriate survey coverage and data collection that encompasses the niches of the species, and sort of cautions against extrapolating these relationships into low or unsampled areas, especially if the environmental conditions of that region are different. The next assumption I will discuss is the criteria for inclusion and exclusion. So temperature is known to be an important factor of lobster habitat. When ignored, the forecasted habitat suitability changes were less severe. So we underestimated the impact of climate change on habitat. Now remember, the red in this map here means that these areas have a higher HSI in the future than the base case predicted. Now, a management framework that neglects effects from important covariates may not be prepared for changes in population dynamics and spatial domain that could arise. So when it comes to determining whether or not a parameter warrants inclusion as a covariate in these HSI calculations, RMSE or other model fitting metrics may not actually be appropriate in bioclimate modeling and may actually lead to modeling mischaracterization. Figuring out the important variables in habitat modeling is a common problem, a very common problem, simply because there's no substitute for a priori knowledge of the species. So next, I will be discussing the separation of life history data. So in the study, we looked at three different effects of life history subgroupings: combined versus separate seasons, combined versus separate sexes, and combined versus separate life stages. So let's look at each of these and see what we learned. When looking at separate seasons, spring HSI seems to decrease over time, but fall HSI seems to increase in many areas. But the strength of spring decrease is larger, however, and thus overall suitability declines over time. These seasonal influences, though, which could have profound effects on the fishery, are not apparent when you ignore this seasonality. When looking at separating sexes and life stages, we didn't actually see many differences. These difference plots are near white, indicating very small differences between these and the base case. Now, this may point out that seasonal or temporal differences heavily outweigh differences between sexes and life stages, but a myriad of literature indicates differences in habitat usage between sexes and between life stages. This doesn't necessarily disagree with that literature. It's simply indicating that this information may not be as necessary when modeling habitat, as other variables are far more important, like seasonality. The good thing is, though, these separations of life history are easier to determine the importance of because these tests can be explicitly done. These difference maps now become a direct measure of whether or not separation is needed. And the last assumption I will discuss is about extrapolation data. So we used, as I said before, FVCOM data for temperature and salinity. This is modeled data. What if we used a different data set? So we tested interpolated environmental data to keep its observational nature. And this was a Krieg field that's been used in some previous work by Kevin Friedland. It's a combination of annual data coupled with climatological data to estimate bottom temperature and salinity fields. Now, these data took the place of the environmental data throughout the entire bioclimate framework. And this map was generated, again, representing differences from the base case future estimates. Now, we can see differences, but they're a bit harder to determine why. We see overall higher HSI estimates in the inshore areas, lower estimates in deeper waters. This essentially means that spatially, these data produce more uniform estimates of future HSI than the base case did. So is this more realistic, or is the base case? That question is pretty hard to answer. Discrepancies between these types of data sets are common, but it's often hard to determine the reason for the discrepancies. Regardless, the important takeaway is that choice of data does matter and it will affect the end results. So why did we do this? What were the larger conclusions? What was the benefit of it all? Well, first, we did this analysis on lobster because it's one of very few species on the planet with such a high level of detailed survey data across a large and detailed spatiotemporal extent. Because of this, we know much of what is right for lobster a priori. So many of the tests, the changes that we made were done so knowing that they were wrong. And in comparing these tests to the base case, there are differences, but there's no actual way to tell if it was more right or more wrong from a statistical or modeling perspective. There's no way to determine any sort of an accuracy. And so this work now serves as a caution to mapping and forecasting habitat for any species. There needs to exist high confidence in modeling assumptions a priori. If not, then results may appear accurate, but could be biologically unrealistic and lead to false assumptions about the future of the species. So all in all, yes, this type of work is necessary moving forward, but can only be appropriately done with high model-based species. Okay, with that, I have a lot of people to thank here: advisors, committee members, co-authors, family, friends, general mental support staff over the years. I'd also like to thank the University of Maine, Stony Brook University, the Maine DMR, New Hampshire Fish and Game, Massachusetts DMF, and Rhode Island DEM. And special thank you to NOAA and Sea Grant for providing the funding for this work under the National Marine Fisheries Service National Sea Grant Population and Ecosystem Dynamics Graduate Fellowship. And of course, thank you, Kristen, Lisa, and everyone who works on putting these seminars together.
And thank you. That was great.
Yeah.
So we have lots of time now. We have about 10 minutes for people's questions, and I encourage you to ask them. Please, if you have one, look at your panel and just type it up in the questions chat box, and I'll read them to Cameron. And for those who might have joined us a few minutes late, Cameron did share his slides with us. By the way, they were beautiful, really beautiful presentation. So please feel free to download them, also from the handouts menu in the control panel. And last but not least, in terms of bits of information, please share this presentation. We have recorded it, and it will be available in the NOAA Central Library YouTube channel, which I put in the chat, but I will add to the chat one more time in case you know of anyone who'd be interested in Cameron's work. So with that, we'll take a second to wait for any questions that might arrive.
Lisa, can I jump in here with a question?
Absolutely.
So Cameron, jumping back to the first part of your presentation, surveys are kind of a hot topic right now in NOAA fisheries, and I'm wondering if there are any conclusions that we might be able to draw regarding the need for survey data in terms of like survey coverage or frequency from the work that you did. I thought it was a very interesting conclusion that you came to about the use of indices and the relative large amount of survey data that's available for lobster versus other species. So I'm just sorry to put you on the spot. That's kind of a hard question. I'm just wondering if you have any thoughts there.
No, yeah. So I think first and foremost, just to reiterate again, because I think it's incredibly important, is that the results for lobster themselves are just for lobster themselves. So as far as whether or not whether or not environmental parameters are needed in these survey indices is definitely going to vary between species, between assessments. And so individual tests are necessary for different species. That said, as far as survey coverage or whether or not something is accurately, or whether a survey accurately covers the niche of a species, I think that's more a question for simulation-based techniques. I know here in the Chen Lab, what we've done before is we've sort of used survey methodologies on simulated populations, and we've sort of tested different levels or different spatial extents of these surveys to see at what levels we can generate the same results and the same findings, so that we don't, overspend or overdo surveys when we can have smaller surveys that would give us the same amount of information. Yeah, does that answer your question?
It does, yeah, thank you. Appreciate your thoughts there.
Yeah.
And while you were answering that question, another question came in. This question asks, do you have a hypothesis for which type of species assessments might benefit inclusion of environmental variables?
Which species assessments might benefit from the inclusion of environmental variables? I think there's going to be two answers to this. The first one is the broad answer of potentially all of them, but the second answer, it's definitely going to vary. I think that species like crustaceans, because their physiology is so influenced by the environment, their life history parameters like growth, like recruitment and everything like that, those are going to be heavily influenced by fluctuations in the environment, by fluctuations in temperature and salinity. And so that's actually some other work that we've been looking into is how we can incorporate these fluctuations in these life history parameters into the stock assessment process through things like growth and size and maturity. And I think that those are going to be important for species like crustaceans or other ectothermic species where their internal physiologies are heavily impacted by the environment. That's not to say that other assessments like sort of, the other end of the spectrum, if we go tuna, they're still going to be impacted. Their migrations and things like that are still tied to the environment, but their internal physiologies are less impacted by these small changes. They're still going to be impacted, but I think the areas in which you would include environmental effects into the stock assessment process, into the framework, would be different than the areas in which you would try to incorporate them for species like lobster or crustaceans. So short answer, pretty much all of them probably, because everything is impacted by the environment in some way. But the long answer, it's going to differ depending on different types of species.
Thank you. I don't see any more questions, so I guess we'll go ahead and wrap this up. How do you feel about being emailed, Cameron?
Yeah, go right ahead. Anyone can shoot me an email if they have any more questions.
Awesome. Okay, yeah, there it is, cameron.hodgdon@stonybrook.edu. I really appreciate your presentation today. And Kristen, as always, thank you for organizing the National Stock Assessment Science Series. I hope everyone will join us again for a NOAA Central Library National Stock Assessment Seminar. We host them every first Thursday of the month at 3 p.m. Eastern Standard Time. And we'll have one in July. So thank you very much and enjoy the rest of your day, everybody.